Good evening, dear all. Welcome to the physics revision session, rapid revision session. So today we are going to the first 5 chapters of our NCERT textbook. What is the importance of this first 5 chapters? You know, we have 3 5-mark questions in the board paper. Out of that, 1 5-mark will be sure from this first 5 chapters, and out of 3 mark you can make sure that 2 3-mark questions sure from first 5 chapters, and we have 7 2-mark questions, and we have 18 MCQs. A big volume of MCQs and 2-mark questions are definitely coming from this first 5 chapters. So we are starting each chapter one by one with a mind map. So what is the mind map means? You know, mind map gives overall idea of the chapters. So each chapter where we have to focus, which are the important terms, which are the important equations, everything is there in this mind map. You can watch this video later, or you can take the screenshot of the mind map and take a poster, and that is, will help you to catch the chapter at a glance. Now we are explaining the first chapter mind map. So see, the first chapter, electric charges and field. What are the important concept of electric charges and field? So first of all, electric field, and electric field lines. So now electric field lines properties are there. You can see always normal to the conducting surface, originating from positive charge, terminating at negative charge, never intersect each other, do not form closed loops, or imaginary lines. So these are the properties of electric field lines. Now we can say electric field due to the point charge. So what is the electric field due to a point charge formula? K Q by R square. K is 9 into 10 raised to 9. So that is 9 into 10 raised to 9 Q by R square. SI unit is Newton per Coulomb. Then we have a superposition principle, force between multiple charges. We have a electric field due to a dipole. So axial one, equatorial one. Very important 2 derivations: axial derivation, equatorial derivation, torque derivations. See the right bottom corner, there is 3 things. These 3 things are very important derivations coming for examinations. And another important point, the big backbone of this chapter is Gauss theorem. The last of the chapter, Gauss theorem is there. Statement of Gauss theorem is important. And in the same manner, applications of Gauss theorem. Again coming derivations. We have the very important derivations here. 3 derivations on the left bottom box. So see, the right bottom box there is 3 derivations, and the left bottom box there is 3 derivations. Total in the chapter 6 derivations are there in the chapter electric charges and field. So here basics of electric charge, the quantization of charge Q equal to Ne, SI unit of charge, and charge is a scalar quantity. This is the basic idea of the chapter 1. We'll go through the questions before completing all this important mind map. Will come to one by one each chapter, highly possible and probable questions that is coming for the upcoming physics board examination. So I think you all have an overall idea about the chapter electric charges and field. Now we are going to the next chapter, electrostatic potential and capacitance. This is actually a tricky chapter. There are lot of conceptual questions from this chapter. Compared to the chapter 1, in this chapter number of derivations are less, but conceptual ideas, brainstorming questions are important from these chapters. So first of all, we are talking about electric potential. Name of the chapter is that electric potential. Definition we have SI unit, and then we can say electric potential mapping is there, equipotential surface. So equipotential surface properties are there. So component of electric field parallel to an equipotential surface is always 0. And another important point, electric potential we want to study. That is the first one, potential due to a point charge, the one derivation. Potential due to a dipole, the next derivation. The left top corner, two derivations, which are potential due to a point charge, potential due to a dipole. Now we are going electric potential energy. Rather than the definitions, the questions are coming basically numericals for potential energy. Potential energy, all the ideas are there highlighted. And then we have capacitance. The chapter we can divide into two parts, electric potential, and the next one there is capacitance is there. So capacitance, there is the derivation for capacitance. When a dielectric slab is inserted, what is the capacitance? You can see the right top corner, the capacitance when a dielectric slab is inserted, that is one derivation is there. And then what is the basic difference between conductors and insulators? It is there correctly. Electric field inside a conductor is always 0, and electric field is always perpendicular to the surface of a conductor. In static one, there is no additional charge inside the conductor. Give reason questions. Give reason questions. Dear students, please see the right bottom corner, 3 points. Why electric field is 0? And next one, why field is perpendicular? Why no charge is inside the conductor? Give reason questions. 3 give reason questions important. Now we are talking about potential energy of a dipole. We have a theta 90, so potential energy formula minus P dot E is there, the potential energy. Capacitance related circuit problems are there. So in our board examination, last 5 years if you are analyzing, capacitance based circuit problems are there, always coming for 3 mark. 3 mark questions are there. Series combination, parallel combination, and then energy stored in capacitor related numerical problems are there. So this is the idea about the second chapter. So at a glance, if you are saying for the second chapter, we have basic part of potential and the part of capacitance. So that's about our second chapter. Mainly the derivations I said, 2 derivations for potential and 1 derivation for when a dielectric slab is inserted between the plates. In the next chapter, current electricity. Current electricity is a chapter, so it has highest weightage as a single chapter in board examination. A single chapter, it has high weightage. That is the chapter, see, current electricity. So current electricity, many concepts are there. See, look, the arrows are, number of arrows are there here. We have to study resistivity, conductivity, mobility, drift velocity, current density, and then Wheatstone bridge, electric cell, grouping of cell, and Kirchhoff rules. So here, what are the important derivation part? Derivation part is the parallel grouping and series grouping of the cell. So we can say the parallel grouping and series grouping are the derivation part. Same manner, Wheatstone bridge principle is also the derivation part, and we have the relations between them. So first of all, J equal to or sigma equal to J by E is their derivation part. Kirchhoff rule statement is very important. The statement of Kirchhoff rule. So we can say that is loop rule and junction rule. Recall, loop rule is accordance with the law of conservation of energy, and junction rule is accordance with the law of conservation of charge. So we have two rules for Kirchhoff, that is junction rule and loop rule is there. Temperature dependent of resistance, possible areas for MCQs. MCQs are there from this chapter, sure, and that is mostly coming from this one, that is see the resistance variations graph. So we have a current density formula, and we can say that Wheatstone bridge already explained. Cell, we have three important terms: EMF, internal resistance, and terminal potential difference. What is EMF and what is the internal resistance? The resistance offered by the components of a cell is known as internal resistance. So this about the chapter current electricity, that is a 1 minute revision, important area we completed. Now we are explaining the next chapter, that is the fourth chapter, moving charges and magnetism. According to my last 15 years experience in the board exam field, I can say most of the students are making wrong answers in this chapter, because the determination of direction of force, direction of field, so that everyone has to practice, very important. So can you say that is, suppose we are considering moving charges and magnetism, what are the important area of this chapter? So the first important point of this chapter is, the backbone of this chapter is Biot and Savart's law. Biot and Savart's law statement is there, and Biot and Savart's law we can apply to find the magnetic field due to a circular loop. Same manner, we can say that here there is magnetic field definition is there, and magnetic field due to a single wire, and the magnetic field at a point due to a solenoid, and we can say the force between parallel wires, torque acting, definition of ampere, and then the expected 5-mark question it is from this chapter. I am repeating, moving coil galvanometer is an expected 5-mark questions. Moving coil galvanometer, where galvanometer sensitivity and how we can convert galvanometer into ammeter, how we can convert galvanometer into voltmeter is important. So these are the ideas about the chapter 4, moving charges and magnetism, is the important areas we highlighted correctly. So as a whole, when I am looking to that chapter, it's first coming into my mind Biot and Savart's law, and the second coming to the mind Ampere law is there, Ampere circuit law, and the third is coming to the mind moving coil galvanometer is there, conversions of galvanometer into ammeter and voltmeter is there. So we can say the next one, the last chapter that we are going to explain. Thank you. So dear, see look, the last chapter, magnetism and matter we are explaining. So magnetism and matter, that is chapter 5, it's a very small chapter, not that much derivations, only very few ideas are there. Earth magnetic field section is deleted. So we can say for magnetism and matter chapter, first of all, solenoid is equivalent to bar magnet. No derivation for this, we can study the formula only. No derivation for this. Potential energy, no derivation. Torque, no derivation is there. Only formulas. And then magnetic terms are important. There on the right side you see three terms: intensity of magnetization, magnetic susceptibility, magnetic permeability, magnetic intensity. These three terms, it should be clear for us, with the units, with the definitions, and significance, physical significance also. For example, suppose I am saying the susceptibility of the material A is greater than the susceptibility of material B. What does it mean? If chi A greater than chi B, what does it mean? It means that the material A will magnetize more than B when both are kept in the same magnetic field. The material A will magnetize more than B when both are kept in the same magnetic field. Now we have magnetic substance. See, suppose we are considering the three magnetic substances are there: para, ferro and diamagnetic substance. Examples are important. So aluminum, manganese, iron, cobalt, nickel, bismuth, copper, mercury and silver is there. So these are the important ideas about the magnetic substance. So the outline of the chapter that we completed, name of the chapter, magnetism and matter. So we went through all the 5 chapters, important ideas within this short time. Now we are going to see what are the possible questions coming for examinations in the upcoming board examination. We are ready to solve one by one each questions. So which are the 5 chapters that we are covering here? 1, 2, 3, 4 and 5 chapters we are explaining. Questions are in the order of each chapter. So the first question, see what is the first question there? Its question is from the chapter 1. Two identical conducting balls A and B have charges minus Q and plus 3Q respectively. They are brought in contact with each other and then separated by a distance d apart. Find the nature of the Coulomb force between them. So here we are explaining the point here. Two balls are there. So I am marking that is ball A and then we have a ball B. So their charges are given. First ball A has charge minus Q and then ball B has charge, we can say that is equal to plus 3Q is there. Plus 3Q. Now what I am saying, when these charges are, we can say that correctly, that these spheres are identical and they placed in contact. We know when two charged bodies are placed in contact, if they are identical, charge flows from one to another till both acquire same charge. So we can say charge on A is equal to charge on B, that is equal to, we can say minus Q plus 3Q divided by 2 is there. So that is equal to 2Q divided by 2 is equal to Q. So A has a positive charge and B also have a positive charge after they placed in contact. So now they are kept in a distance apart. So the charge of A will be now plus Q and charge of B also will be plus Q, separated by a distance d apart. We know like charges will repel. So the nature of the force, their nature of the force means whether it is repulsive or attractive. So we can say here the force is repulsive. The force is repulsive. So there is a repulsive force is there. Yeah, right. You know, see, many got the right answer. So we can say repulsive force is the nature of the force between them. Keep in mind one important point. I am repeating. See, if their sizes are identical only, we can use this method. If they have a different size, then charge will flow until their potential becomes equal. So we can say here that is their identical size, then charge becomes equal. The first question, I think it is clear for everyone. Now we are doing the next question now. So what is that question? So highly tricky question it is. Take care when you are answering. A point charge is situated at an axial point of a small electric dipole at a large distance from it. The charge experiences a force F. If the distance of the charge is doubled, the force acting on the charge will becomes. So in this question, most of the students are thinking like that, force is inversely proportional to square of the distance. So we can say distance doubled. So force proportional to now 1 by 2 r the whole square. So that is 1 by 4 r square. That is F by 4. But this answer will went wrong. Why it is? So that we are going to explain. The reason is that you can see, look, here the point charge is kept at the axial point of an electric dipole. So we are considering an electric dipole here. Charge minus Q and plus Q. So this is the dipole. Its axial line, the point along the axis. So suppose here we are keeping a charge capital Q is there. So what is the force experienced by this charge now? We can say the force experienced by the charge, that is F is equal to, that we can say F is equal to Q into E is there, E. Where E means it is electric field. So we can say it is Q into E axis is coming. Electric field on the axis of the dipole. So what is the electric field on the axis of the dipole? Electric field on the axis of the dipole is proportional to 1 by r cube. 1 by r cube. So we can say the force is directly proportional to 1 by r cube. First case. It's not 1 by r square, it is 1 by r cube, because here we can say that is the force is proportional to 1 by r cube, because electric field is proportional to 1 by r cube. Now they are saying, so the distance of the charge is doubled. Distance of the charge is doubled. So we can say the new force F dash proportional to 1 by 2 r the whole cube is there. So instead of r I am writing 2r. So that is 1 by 8 r cube is there. So you can say F is proportional to 1 by r cube. So this is F by 8. Yeah, right. Many students answered right. It's good. I'm not calling the student's name here, see, because lot of students answered the right one correctly, and the right option is F by 8. F by 8 is there. So I think this question is clear for you. Sir, NCERT questions, or this is PYQ. It's a previous year questions. It's a previous year question and most possible question for examinations. So here the electric field relation is there. It is proportional to 1 by r cube. So force is proportional to 1 by r cube is there. So that is the second question that we completed. Now we are going to explain the next question. Question 3. Find the orientation of the dipole relative to the electric field for which torque on it is maximum and half of maximum. So the question is based on torque acting on a dipole. I told in the chapter 1, torque acting on a dipole is a very important derivation. You all have the equation for torque acting on the dipole. So what is the formula for torque acting on a dipole? Torque acting on a dipole is equal to P is sine theta. Torque acting on a dipole, P is sine theta. Now they are asking, in which orientation relative to the electric field torque will be maximum? So we can say if theta equal to 90 degree, theta 90 degree, then torque is equal to PE sine 90. Sine 90 is the maximum value of sine. So we can say that is equal to PE. So that is the maximum torque. Maximum torque. So what's the orientation? Theta 90. So we can say if the dipole is, we have to say our answer by word. If the dipole is perpendicular to the field, then torque will be maximum. Torque will be maximum. So the first one we completed. Now the second one, when it will be half maximum. Dear, half maximum, it's a question. When sine value becomes half, that is a half maximum, because maximum value is P. So when it becomes a half maximum, yes, right, it is 30 degree, maximum will be half maximum is coming. So we know the picture now. If theta equal to 30 degree, we can say torque is PE sine 30. Sine 30 1 by 2. So I can write that is equal to PE by 2. But PE is tau max. So I can write that is tau max divided by 2 is there. So torque will be half of the maximum when it is at 30 degree. But most of the students may have a confusion about that, because when theta 0, torque is 0. Theta 90, torque is maximum. So by logic, some students may think theta 45 half maximum. Not like that, because sine 45 is not 1 by 2, it is 1 by root 2. So half of the maximum value coming when theta is equal to 30 degree. So that is question 3. Now we are explaining question 4 now. How does the electric flux due to a point charge enclosed by a spherical Gaussian surface get affected when its radius is increased? A repeated question in the exam, and textbook back this idea is there. So already we know that the total electric flux passing through a closed surface is equal to 1 by epsilon 0 into the charge enclosed. So you can see the flux passing through a closed surface depends only on two things. Which are the two things? The charge enclosed and the medium in which the surface kept. So we can say it depends upon the charge enclosed. Charge enclosed. And next one, the medium in which the surface is held. So we can say the closed surface is kept. Closed surface is kept. Whether it is kept in air or whether it is kept in liquid. So phi closed depends upon these things only. Radius larger, radius smaller, doesn't matter. So we can say the flux remains same now. So flux will remains the same. So we can say there is no change in this picture. Flux remains the same. So this is an important question based on Gauss theorem. Now we are explaining question 5. This question 5 is the chapter 2 question actually. Second chapter question. Electric potential and capacitance chapter. So the question I am explaining here, look. The work done in moving a charged particle between 2 points in a uniform electric field does not depends on the path followed by the particle y. So actually this question teaches an information also. It gives an idea also. What is that? Suppose I am considering there is a point A and there is a point B. A charge is moving from the point A to point B. How much is the work done? How we can calculate? For example, a charge Q0 is moving from the point A to the point B. How much is the work done? Work done to move a charge from the point A to the point B is equal to the moving charge into the potential of the final point minus potential of the initial point. So it depends only on three things. What charge you are moving. And second one, we can say potential of the initial point, potential of the final point. So here, yes, right. So we can say, look, suppose I am considering a path like this. So can you say here also same only? You can see that here work done to move the charge from A to B. The charge moving, suppose Q naught. Initial point is A, final point is B. So whatever may be the path, work done remains the same. Work done to move a charge, listen here, work done to move a charge between 2 points depends on the initial and final point potential and also the charge only. So why it is? That's the question here. Why it is? Why it is? We studied in our first year class and we studied even in chapter 1 that concept. Electrostatic force is a conservative force. We know that idea. We wrote that point. So what is electrostatic force is? Electrostatic force is a conservative force. Do you know what is the meaning of conservative force? A force which is work done by that force is not depends on the path taken. Work done by that force is not depends on path taken. Such forces are called conservative force. So electrostatic force is a conservative force. So work done is not depends on path taken. Therefore we can say work done not depends on the path taken. Not depends on the path taken. There occasionally I can say one important question. In chapter 1, we studied there is a basic difference between electric field lines and magnetic field lines. You know what is the difference? Electric field line is not a closed loop, but magnetic field line is closed loop. I am repeating, electric field line is not a closed loop, but magnetic field line is closed loop. Why? The question is there. Give reason question. Chapter 1. Why electric field is not a closed loop? Why electric field is not a closed loop? The answer is that why it is not a closed loop? Because electrostatic force is a conservative force. So this statement is very important. I am repeating there once more. Look, the electric force is a conservative force. That is why no work is done when we are moving a charge between 2 points. The work done is independent of path taken. Same manner, electrostatic field lines is not a closed loop because electrostatic force is a conservative force will be there. No, monopole. Someone are asking this point correctly. Look there, monopoles are not possible. That is for magnetic field lines, not electric field lines. Electric field lines, monopoles possible. Single positive charge and single negative charge possible. So this is the answer. Electrostatic force is a conservative force. So now the next one. So this answer, please see, very important one. Now we are explaining the next one. Look, question 6. 2 point charges Q and minus Q are located at points 0, 0, minus A and 0, 0, A respectively. There, that question, when we are reading, students will think minus Q and plus Q. So it is what? Equal and opposite charges. So it is a dipole. It's a dipole. So we can say that, the 2 point charges Q and minus Q. So definitely it will be a dipole. So I'm marking now the dipole here. So look, first one charge Q and here we have a charge minus Q. Charge Q is at 0, 0, minus A. So coordinate 0, 0, minus A. Charge minus Q at 0, 0, A will be there. Now they are separated. So it is a axis now. This is Z axis. You can see the coordinates. It's Z axis. And here we can say this is the origin of the Cartesian system now correctly. So what is the separation between them? This distance is minus A because it is left. But when we are talking about the distance, it is A only. Same manner, this distance is plus A because it is on right. So what is the total separation? Total separation is 2A is the total separation between Q and minus Q. So the two charges separated by a distance 2A. It's a dipole. Now they are asking, first question, find the electrostatic potential at 0, 0, Z and XY 0. See, please take care, look. What is 0, 0, Z stands for? 0, 0, Z means it is a point on Z axis. We can say that is the dipole is along the axis now. Dipole is along the X axis. Along here, look, 0, 0, minus A, 0, 0, A. So the dipole is along Z axis. And your point is also, suppose I am marking the point here. The point P is there. And that is, we can say the coordinates 0, 0, Z is there. So this point P is along the Z axis, or we can say along the axis of the dipole. We know what is the electric potential on the axis of the dipole. That is V axis. V axis formula. We know formula we are ready to write. That is 1 by 4 pi epsilon 0 P divided by R square. So that is the potential on the axis of the dipole now. So we can say what is the P value here and what is the R value here. P is, we can say that is electric dipole moment, product of charge and separation. So Q into 2A. So I can write 1 by 4 pi epsilon 0 Q2A divided by. And here we can say distance. What is the distance to the point P from the center? So we can say the distance is Z because the point is 0, 0, Z. So Q2A divided by Z square. So V axis is equal to 1 by 4 pi epsilon 0 Q2A divided by Z square is there, V axis. Now they are asking potential on another point also. What is the potential on another point? XY0 is the point there. Do you know? You can imagine what is that XY0 here stands for. Suppose the dipole. Dipole is on Z axis. So XY0 means that is in XY plane. You can see it is in XY plane. XY plane means it is very clear. It is the equatorial plane of the dipole. So XY0 is, we can say XY0 is a point on, it is a point on equatorial plane. It is a point on equatorial plane. If the equatorial point are there, what is the potential? So the potential on the equatorial point is 0. So we can say V equatorial is equal to 0. We studied that point. The potential due to a dipole on equatorial point will be 0. So V equatorial is 0. So this XY0 point potential will be 0 is there. Now the B part of the question. See, please see the B part. What is that B part? How much work is done in moving a small test charge from the point 500 to minus 700 along the x-axis. So we can see that question now correctly. Look, the point is given here. Look, this is our dipole and here the coordinates are marking once more. So here plus q is there, 0, 0, minus a, and here minus q is there, 0, 0, plus a. And here, the points is given on which axis? See, 5, 0, 0 is there. It is x-axis point. Minus 7, 0, 0, that is negative x-axis point. So I can mark that point here like this. So we can say this is the x-axis point now. So x-axis is which plane? Equatorial plane. So the potential on the equatorial plane is equal to 0. So B part we completed, that is potential will be 0. And here there is a shortcut that I am explaining. Suppose questions are coming based on work done. In the case of a dipole, coordinates is given, definitely answer will be 0. For the last 10 years in the board examination, questions came, answer will be 0 only. So it's a short idea you can recall. So I'm explaining once more the point, how sir it is equatorial one, depends upon the axis of the dipole. So for example, suppose 3, 0, 0 and minus 3, 0, 0 are the two charges. Here plus q is there and here minus q is there. So dipole is on x-axis. Now any point on y-axis, any point on z-axis will be equatorial point. So work done will be, if you are considering, or the potential will be 0 is there correctly. So if potential is 0, in the question what they are asking, potential 0, what is the work done? So the formula for work done we have, that is the work done to move a charge. Suppose this point is I am marking, that is equal to 5, 0, 0. This point I am marking, minus 7, 0, 0. So here the point is suppose A, the point is B. I am moving the charge from point A to B. The charge Q0 is moving from the point A to the point B. So what is the work done? WAB is equal to the charge into VB minus VA is there. But look, VB and VA are 0. So answer will be 0 is there. Q0 into 0. So answer will be 0. So we can say, tell me what's the point there correctly? Right. One small request, 7:30 in India. Okay, no. Okay. Now see that you can contact. Yeah, it's correct that you can contact with the brilliant authorities. See they will solve the issue. Okay. Now we can say WAB is 0 is there. Work done to move the charge from A to B along the equatorial plane is 0. Now we can have the next question now, that is question C. I think you will be answering this question. Question C. What is option C? Please look now the C part of the question. How would your answer change? I think all students, for those they are in the chat box, please give me the answer and give the confidence. How would your answer change if the path of the test charge between the same point is not along the x-axis but along any other random path? So what's the point here? Look, we can say that instead of this A and B straight path, suppose a path like this moving, how it will change? Yes, right, see, Dhruvil, the right answer you said, we can say it will not change. Why it is not changing? What's the reason? Because we know electrostatic forces, can you recall that point? Can you recall that point? Electrostatic force is a conservative force. So it is not depends on path taken. So yes, Sania, right. Yes, Faris, right. Yes, Nidin, right. Yes, Samu, right, correctly. So Adil, Rafiq, right. So we can say that is from A to B, any path you are taking, doesn't matter. So work will be 0. No answer change will be there. The answer will remain same. Answer will remain same. Answer will not change, it will remain same actually. So this is the point, very important correctly. See, yes, IIT aspirant and fake flip-flop, I don't know what's that name correctly. So everyone give the right answer correctly, so answer will remain the same actually. So these are the points about the dipole, conceptual points. I'm repeating once more, please listen here what I said. Axis potential is 1 by 4 pi epsilon 0 p by r square, and equatorial potential is 0, and work done to move a charge along equatorial of the dipole always will be 0 is there. It is not depends on the path taken. Now we are going to the next question. See, this question is very important question. That is why I included in this class, for a live class, to make the class more active. We can small concept we can add, but I cannot avoid this question because it is such an important question for the upcoming board examination. I am saying it is one of the golden question for March 6th exam. So look, 3 concentric metallic shells, A, B and C. Question is little lengthy, solution will be lengthy, expecting a 3-mark question. Now look, radii A, B and C, A less than, B less than C, have surface charge densities sigma, minus sigma and sigma respectively as shown. Obtain the expression for the potential of 3 shells A, B and C. So first of all, I want to find the potential on the surface of the shell A. Dear, to find the potential on the surface of the shell A, how we will calculate the potential? Potential on the surface of the shell A means it is the total potential on the surface of the shell A. So whatever the charge present, wherever the charge present in the diagram, all charge I want to consider to calculate the potential. One more point we have to recall, potential is a scalar quantity, so we have to add them to get the total potential. So I can say the potential at the point on the surface of the shell A, V on the surface of the shell A is equal to, so there is potential due to the charge A, same manner there is potential due to the charge on the shell B, there is potential due to the charge on the shell C. So there is 3 charges, QA, QB and QC. That charges are distributed on the surface of the spheres. So we can say potential on the surface of the shell A is equal to, I am writing in detail, so potential due to the charge of shell A plus potential, so please see, potential due to the charge of, for those the students see, please write with me, charge of shell B plus the potential due to the charge on the shell or of the shell C. Now we have 3 potentials here. So in order to find the potential due to the charge, I wrote due to the charge. So I want to find a charge on each shell. So first of all, what is the charge on the first shell? Look, sigma given. So we can say for the shell A, charge density is equal to charge by area. So we can say that is, from this idea, Q is equal to sigma into A. So now QA, charge on the shell A, sigma. What is the surface area of the shell A? Its radius is A. So we can say the surface area will be 4 pi A square. So QA sigma 4 pi A square. See the question, for the second shell it is minus sigma. So QB will be minus sigma into 4 pi B square. Now we have QC. So the charge on the shell C now. that is equal to, it's already sigma given. So I can write sigma into 4 pi c square is there. So we have all the three charges now. So I'm ready to write the total potential equation now. So please see, look, VA is equal to potential 1 by 4 pi epsilon 0 QA, that is the charge on the shell A, QA, its radius is A given, plus 1 by 4 pi epsilon 0 QB by B, plus 1 by 4 pi epsilon 0 QC by C is there. Now we are replacing all these values now. So I can take a 1 by 4 pi epsilon 0 into QA value sigma 4 pi A square by A. Then there is a minus sign because QB is negative. 1 by 4 pi epsilon 0 sigma 4 pi B square by B, plus 1 by 4 pi epsilon 0 sigma 4 pi C square by C is there. So we can cancel the terms now here. So we are cancelling the term. So 4 pi cancels, A square A cancels, 4 pi B square B, 4 pi C square C cancels. So what are the terms coming now? VA is equal to, look here, sigma by epsilon 0 is common in all the term. A minus B plus C is there. So this is the potential on the surface A now. So the potential on the shell A, sigma by epsilon 0 into A minus B plus C is there. They are not asking the potential on the surface of the shell A alone. What is the potential on the surface of the shell B we want to find. So how we will find VB now? So same manner we are writing. So what is the formula? 1 by 4 pi epsilon 0 QA by B plus 1 by 4 pi epsilon 0 QB by B plus 1 by 4 pi epsilon 0 QC by C. So you may ask this question to me, I know. Sir, why you write QA by B? Why you write QB by B? Then why you write QC by C? What is the reason for QC by C? And why it is QA by B? Dear, we studied a very important point in potential. What is that? If this is a shell now, on the surface of the shell, suppose the potential is 20 volt. And anyone can say what is the potential at the center of the shell? That is also 20 volt. 20 volt. Why 20 volt? Because we can say potential remains the same everywhere. Potential remains the same everywhere throughout the conductor. Throughout the conductor. So I'm talking about now, you can see I'm talking about the shell C now, shell B here. So shell B, and we can say the shell A is inside. Shell A is inside. So the potential here will be same as on the surface of the shell. So even though you have a charge here QA, then I'm taking the potential on the surface. So it will be B. So QA by B, QB by B, and QC by C will be there. Why sir QC by C? Because C is outside. For the shell B, C is a point outside. Outside it is not correct because surface and inside will be same. Potential inside everywhere is equal to on the surface. Outside potential is not same as the inside one. So we can say this is QC by C only there. Now I am substituting the values now. So it's coming 1 by 4 pi epsilon 0, that is K value, QA sigma 4 pi A square by B plus 1 by 4 pi epsilon 0, there is a minus sign. So we can say here the minus sign, and 4 pi B square by B, and here plus 1 by 4 pi epsilon 0 4 pi C square by C is there. So substituting, cancelling the terms. 4 pi cancelled. Here 4 pi cancel. 4 pi cancels. 1c square and 1c cancels. 1b square and 1b cancels. So we are getting the final equation for VB now. VB equal to sigma by epsilon 0 into. So here a square by b not cancelled. Now here b square by b is coming, and here c square by c, it is c is there. So that is VB. That is VB. So in the same manner, I want to find VC also. So we are explaining how I will find VC. So in the case of VC, there A is inside, B is inside, C is the shell now currently. So what is the formula? QA by C. Inside is same as on the surface. So QA by C, QB by C, and QC by C will be there. So I can write the potential on the surface of the shell C is equal to 1 by 4 pi epsilon 0 QA by C. QA by C. I'm writing now. So please see, QA by C plus 1 by 4 pi epsilon 0 QB by C, and here plus 1 by 4 pi epsilon 0 QC by C is there. So we are substituting the values now. 1 by 4 pi epsilon 0 QA sigma 4 pi A square by C, and minus 1 by 4 pi epsilon 0 QB value. So what is QB value? Sigma 4 pi B square by C, then plus 1 by 4 pi epsilon 0 sigma 4 pi C square by C is there. Now we are simplifying. 4 pi cancels. Now it's coming sigma by epsilon 0 into A square by C minus B square by C. This C and this C cancels, plus C will be there. So this is VC now. So very important idea we are explaining. Potential inside will be same as the potential on the surface. That is why for the shell C, I'm taking A and B are inside. So I'm taking radius as C. For the shell B, A is inside. So I'm taking that is equal to QA by B. QA by B. So we calculated all the potentials here. So when we are back the questions, they are asking second part of the question. If the shells A and C are at the same potential, obtain the relation between A, B and C. So we have to deduce the relation between A, B and C if shell A and C are at the same potential. So we are explaining that point now, the B part of the question. So please see, look, what is in the B part? It's given potential at the shell A is equal to C. This value given, VA equal to VC. Now what is VA? VA value we calculated just before. What is VA value? Sigma by epsilon 0 into A minus B plus C. So I'm writing sigma by epsilon 0 into A minus B plus C. What is VC? VC is sigma by epsilon 0 into, you see, A square by C minus B square by C plus C is there. So here you can cancel the terms, look, you can cancel the terms sigma by epsilon 0 on both sides. And here plus C and plus C also cancelled. So it's coming, that is A minus B equal to A square minus B square by C is there. A square minus B square is what? A plus B into A minus B. So I can write A minus B is equal to A plus B into A minus B divided by C. So here this A minus B cancels. So we are getting A plus B is equal to C is there. So this is the relation between AB and C when VA and VC are equal. So there This question, this question came many times in the examinations. Yes, right. Yeah, it seems a JE like good one. That comment I like actually. It's a JE type question. But I'm saying there, March 6th, Shamim is saying to you, March 6th, when you open the question paper, there will be some questions that is unseen questions. That question you never see before. So, in order to break that questions, we should have thorough knowledge about the previous papers. Previous papers we want to focus. Many times we informed the students and requested the students like that. We want to practice previous papers, not any other sample papers. On the net, on many websites and many book, lot of sample question papers are there. Don't practice them. Don't waste your time. Go to real CBSE previous year questions. The board papers that is available in many websites. CBSE Gauss, where it is, see that previous year question bank is there. Our worksheet, brilliant worksheet is completely focused on previous year questions. We are updating. Till today, we updated in the group as revisions 8 chapters, all previous year questions. Students are doing them one by one and practicing them. That's very important. So, questions are very important. Don't give up the questions as it is very important for exam. So, there I'm explaining the highlight here once more. Look, suppose we have 3 spheres. Okay, A, B and C. How I will write the potential on B now? Potential on B, A is inside, so take the radius B. B also take the radius B, but for C outside, take the radius C. So QA by B, QB by B, plus we can say correctly QC by C is there. This is the point for the potential on the surface correctly. Very important question. Okay, we completed that. Now we are explaining the question 8 now. So please see what is question 8. Find out the amount of work done to separate charges at a infinite distance. Here the charges are given. I think you can see the question correctly here. Minus for Q, 2Q and 2Q given. And the separation is given L. They are asking, what is the work done to separate them into infinite distance? There we studied what is potential energy of a system of charge. Potential energy of a system of charge is the amount of work done to bring the charges from their infinite points, infinity, to their respective location. So that is potential energy, bringing them together. How much work is required? That is potential energy. Okay, but they are not asking that here. They are asking to separate them. Separate them. So in order to separate them, what is the work done required? It is the negative of potential energy. I am repeating once more. Look, potential energy is defined as the amount of work done to bring the charges from infinity to their respective locations. So, what is the work done to separate them? You are bringing them together. To separate, what is the work done required? It is negative of the potential energy. So, we can say the work done here is equal to the negative of potential energy. So, there is 3 charges. So, how we will find the potential energy? Potential energy equation, we know minus sign already I wrote. 1 by 4 pi epsilon 0 I can take outside. We studied for calculating potential energy taking all the possible pairs. So, we have the formula Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q1 Q3 by R13 is there. Here the charges are given. So if this question is coming in exam, you have to draw this diagram into your answer sheet. Any diagram question, I am repeating, any diagram question coming in the paper, that diagram you have to draw to your answer sheet neatly. And then I didn't assign what is Q1, Q2. So I want to assign them. So I'm assigning the values. What is Q1? So I'm taking this is Q1. That is our order. We can take anyone. Doesn't matter. So this is I'm marking Q2 and this is I'm marking Q3. So then I'm substituting the values now. So it's coming minus 1 by 4 pi epsilon 0 into Q1 is Q. So Q and Q2 is minus 4Q divided by, look, it is an equilateral triangle, infinite distance. So now look, this separation is already given, it is L. So I can write L plus Q2 is minus 4Q and it is 2Q. R23 is L and plus Q1 is there, that is Q, and Q3 is there, 2Q divided by L. So here we can say Q into minus 4Q, minus 4Q square by L, and here minus 8Q square by L, and it is 2Q square by L is there. So I'm writing that value now correctly. So please see, that is the work done, or U is equal to minus 1 by 4 pi epsilon 0 into, in this one, first one, minus 4Q square by L, minus 4Q square by L, plus, and here minus 8Q square by L. So that is minus 8Q square by L plus 2Q square by L is there. And here, you know, minus 4Q square minus 8Q square minus 12Q square minus 12 and plus 2Q square, 10Q square is coming. So minus 1 by 4 pi epsilon 0 into minus 10Q square by L is there. Minus and minus cancelled. So 1 by 4 pi epsilon 0, 10Q square by L is the work done. Work done. So we can say correctly, the work done is negative of potential energy. So we can write, that is the work done here, that is equal to, so W is equal to 1 by 4 pi epsilon 0, 10Q square by L. Repeating once more, the work done required to dissociate a system is negative of potential energy. How to find the potential energy? Take all possible products. Take all possible products. So I'm giving an additional point. If we have 4 charges given, so here Q1, here Q2, here Q3 and here Q4. Can you say to find the potential energy, how many terms will be there? How many terms? 6 terms will be there to find the potential energy. Why 6 terms? What are the 6 terms? Q1, Q2, 1 term. Q2, Q3, another one. And Q3, Q4, another one. Q4, Q1. Then 2 diagonal terms are also coming. What's a diagonal term? You know, Q1, Q3, 1 term. Q4, Q2, another term will be there. So the 2 diagonal term and 4 corner terms. So total 6 terms will be there to calculate potential energy of a rectangular system or a system of 4 charges. A system of 4 charges, we have 6 term will be there. So that's about the potential energy. Now we are explaining question 9. It's so interesting. I think many students can answer this question. What's that? Find the equivalent capacitance of the following network. Here, you know, the 2 networks is given correctly, and we are saying what is the equivalent capacitance of this network is there. So I'm trying for the first network. In the first network, what's the idea there? You know, see, look here, I'm explaining the point. Please listen here. Now look, we have the starting point A and the ending point B. But we know there are some connecting wires. That connecting wires have no capacitance. Simply they marked one wire here and one wire. If these connecting wires are not there, how the diagram will be there? Look, like this. The diagram will be in this manner. This is the diagram. All the 3. So all the 3 are in series. If there is no connecting wires, all the three will be in series. But now what I'm saying, they are connected by a wire now. Look, like this. Connecting wires are there. So whenever we have connecting wires without capacitance, to find equivalent capacitance, we are using the potential reduction method. So we are starting from the point A. So the potential is V1 I am marking. What is the meaning of potential reduction method? Starting point we are marking V1. Now look, when moving like this, here there is no drop. So here also potential will be V1. Why V1? Because when I am moving from here to here, no drop, no potential drop. So here V1, this corner will be V1. But when I am moving for this capacitor, here it will be V2. V2. There is a potential drop because we can say there is a capacitor here. Now when I am moving like this, so here also no potential drop, so V2 will be there. So I am explaining, when we have connecting wires without capacitor, we are using the potential reduction method. It is not the normal method. So we are starting point voltage I am assuming V1. Now there is no potential drop here. So here the voltage will be V1. Now look, across the capacitor there is a potential drop. So it will be V2. Now we can say correctly, we can say that here two are there in this line. Okay. Now see, we can say that here correctly. This one V2. Now down also it's coming V2 because we can say here there is no potential drop. V2 will be there. So now I can redraw this diagram. So how I'm redrawing the diagram now? So you can see that correctly. Look, starting point I'm marking now. Look, starting point is V1. V1. A is V1. Ending point is V2. So starting point is V1, ending point is V2. Now first one, between V1 and V2, there is one capacitor. So I'm connecting between V1 and V2, one capacitor C1. Look, between V1 and V2, there is two capacitors. So I'm connecting two capacitors between V1 and V2. And between V1 and V2, there is one more capacitor. So now this all are C1 now. This is C1, this is C1 and this is C1. Now we can say these two C1 are in series. When capacitors are in series, we can say it is C1 by 2. So C1 by 2, C1 and C1 are in parallel. So what is the equivalent capacitance now? So we can say the equivalent capacitance for the first network is equal to C1 plus C1 by 2 plus C1. So that is equal to, that is, if you simplifying 5 C1, we can say 5 C1 by 2 is there. So many got the answer correctly. Yes, Nitin, you write the answer. So that is, you said before also this answer correctly. 5 C1 by 2 is the equivalent capacitance. 5 C1 by 2. So there I am explaining, whenever we have connecting wires without capacitor, I am using the potential reduction method. So we got it. Now the second question, this one, I think you can try yourself. Just I am marking once more as the diagram now. So you will solve correctly and to get the right answer. So I am ready to draw that diagram now here. Look, we have 4 capacitors. So marking now that 4 capacitors here correctly. So look, the 4 capacitors are marking. The 4 capacitors, each have a capacitance C, and we can say that, look, the point A is there here. So we are marking this point is A, starting point A, and then here there is a connecting wire from the first to last. So we are connecting from the first to last, there is a connecting wire. And then one more, there is a wire from the third one and that point B now. So from the third one, we have a point B now currently. So this is the diagram now. Okay. Now tell me, yes. So many are saying the answer. I will check now currently. Now look. Now it is here also, look, you can see in this network, connecting wires are there without capacitance. Look. So I am using the potential reduction method. So starting point here, voltage V1. If here the voltage V1, of course here the voltage will be what? V1. Because no drop. Now here look, here there is no problem, here all are in one line. This junction is there. So I am marking that is V2. So now we can say, look, if here it is V2, this point also will be V2 now. So look, why V2? Because this point there is no potential. So my starting point V1. So I'm marking now, look, redrawing now correctly. So starting point potential V1, ending point potential V2. So look, first one between V1 and V2 there is one capacitor. So I'm marking one capacitor between V1 and V2, that is C. Look, between V1 and V2 there is 3 more capacitors. So I'm connecting like this. So 3 more capacitors are there in series. So now what's the answer coming now? Look, yes, Dhruvil. Now we can say these 3 are there in series. If 3 are there in series, it is C by 3. C by 3 and C are in parallel. So the equivalent capacitance is C by 3 plus C. So that is C plus 3C by 3, that is equal to 4C by 3. Equivalent capacitance is 4C by 3 is there. There is a shortcut that we studied. If the capacitors are connected in series, if n equal capacitors are connected in series, n equal in series, then C equivalent is equal to C by n. So here 3 are connected in series. So I can write in one step, it is C by 3. C by 3 and C are in parallel. So it is equal to 4C by 3 is there. Yes, Adil, right, then right, Dhruvil, right. Okay, you got the right answer correctly. So that is equal to 4C by 3 is coming. That is the equivalent capacitance. Now we are explaining the next question now. So please see question 10. Question 10 is current electricity questions. So we are going to the important current electricity questions from this chapter now. Now here look, what is the question now currently? Yes, right. How does the mobility of electrons in a conductor change? If the potential difference applied across the conductor is doubled, keeping the length and temperature of the conductor constant. So there is a point. What is actually mobility? Mobility is mu. Mobility is the ratio of drift velocity to the electric field. Drift velocity to the electric field is mobility. Mobility, ratio of drift velocity to the applied electric field. And we can say drift velocity, what is the equation for drift velocity? It has many equations. So now as they are talking about the potential difference, I am ready to write the drift velocity in terms of potential difference. We know drift velocity EV tau by ml is there. So we have EV tau by ml. Then we have electric field. What is electric field? Electric field is C, that we know. How we can write that is in terms of a potential difference. E equal to V by L. So I am writing E equal to V by L. So here, if I am taking the terms are cancelling. So we can say here, look, V and V cancels, L and L cancels. So we are getting the formula, that is mu is equal to E tau by M. E tau by M. So you can see this mobility is not depends on the potential difference. Mobility is not depends on potential difference. So we can say correctly, that is there is no change in mobility when potential difference is doubled, because there is no mobility potential difference term here. V is cancelling. So mobility is independent of potential difference. Mobility is independent of potential difference. So very important point it is. But how it depends on temperature, and point we are explaining correctly. Look how it depends on temperature. You know, when temperature increases, time interval between two successive collision decreases. So when temperature changes, mobility will change. But mobility is not depends on potential difference. It is independent of potential difference. Now we are explaining the next question, question 11th. In the figure shown, an ammeter A and a resistor of 4 ohm are connected to the terminals of the source. The EMF of the source is 12 volt. Having an internal resistance of 2 ohm. Calculate the voltmeter reading and calculate the ammeter reading. This question is for the cell. You know, voltmeter is connected across the cell. So voltmeter means the potential difference across the cell I want to calculate. EMF given, internal resistance given, and external resistance also given. So I can say, look, EMF is given, that is 12 volt. Internal resistance is given 2 ohm. External resistance is given 4 ohm. Now we have to find the ammeter reading, means current. You know, for the cell combination and the cell idea, current is equal to E by R plus R. EMF divided by external resistance plus internal resistance. So we have a E value, that is 12, and capital R is 4 and small r is 2. So it is 12 by 6, that is equal to 2 ampere. So we can say the first part, ammeter reading will be 2 ampere. Then we can find voltmeter reading. So now how we can find voltmeter reading, you know, voltmeter reading means the potential difference across the cell. It's not 12 volt. How we can find the voltmeter reading now? There we have the formula V equal to E minus IR across cell. V equal to E minus IR, potential difference across the cell. So EMF is given in the question. What is the EMF given? That is 12. So we can say 12 minus I value is there, I is 2. So we have a 2 into internal resistance also 2. So 12 minus 4, so it is 8 volt. Very important point in the cell, the potential difference across the cell, terminal potential difference across the cell, E minus IR, where E is EMF, I is current, and we can say R is the internal resistance. Now here, you know, see, look, so we cannot use it's a question, can we use the Ohm's law? Ohm's law we cannot use, because Ohm's law is for a conductor, not for a cell. Okay, now here V equal to 8 volt is there. Now the next one, look, Kirchhoff rule we are explaining. There, you know, just like I said in the question capacitor, you know, Kirchhoff law related questions are also very important for exam. Lengthy question, 3-mark question. I told that is from the first 5 chapter we are expecting, you know, see a minimum of 2 3-mark questions and 1 5-mark question will be there. So this, out of this 3-mark question, it is a most possible question, state Kirchhoff laws and how it can be justified. Then a circuit will given and we have to find the current in the branches. So it is a fit 3-mark question, so that we are explaining now here. So in this circuit we are ready to apply Kirchhoff law. So everyone listen here and look and practice. So what is the point there to find the Kirchhoff rule? You know, Kirchhoff rule here, there are some ideas that I am explaining. in this circuit, the diagram current direction is not given. So not this point. If the direction of current is not given, we are starting from the positive terminal of the highest EMF cell. The direction of current, we are starting from the positive terminal of the cell having highest EMF. So in this example, it's very clear, this 80 volt is the cell having highest EMF. So I'm starting from that. So from the positive I'm starting. So current I. So that current flows like this. So reaches here now. So I'm marking, see that is suppose I1. So I1 current reaches here. When the current reaches here, current will split at the junction C. Because current has two ways to go. So current can flow through CD. Current can go through CF. So the current flowing through CD, I'm marking suppose it is I2. And current flowing through CF, I'm marking that is equal to I3. So that I3 current will be here now, I3 current, and that reaches here. So like this. Same manner, this I2 current will be here. So they will be added now, I2 and I3 added. So what current will be there? I1 splits I2 and I3. So this current will be I1 now. So this is the movement of current, the flow of current that I explained. So now I am repeating once more. If the direction of current is not given, start from the cell having highest EMF. So highest EMF is 80 volt. Starting from the highest EMF cell 80 volt, I am starting the current I1. I1 flows, reaches the point C. It splits into two, I2 and I3. I2 flows like this, I3 in this manner flowing, and I2 and I3 added here and becomes I1. Now what is the next step? Deduce the relation between current in the branches. So we are ready to write the relation between current in the branches. I1 current reaches, it splits into I2 and I3. So I can write I1 is equal to I2 plus I3 is there. That is a relation between the two current. And now we are applying now the loop rule. So we can say I'm taking first the loop, see, for the loop we are saying for the loop A, B, C, D, A. A, B, C, D, A I'm taking A, B, C, D, A. Loop rule when we are applying, there is 3 points we want to take care. So I'm writing loop rule. So what is the idea for this? First of all, LHS will be product of current and resistance. So LHS sigma IR. And RHS will be EMF. Right side of the equation will be EMF. For LHS, there is a rule. If the product is coming in the direction of current, take it as positive. If the product is coming opposite to the direction of current, take it as negative. So for this IR, I can say if it is in the direction of current, positive. Otherwise, it will be negative. Now the next one. What is the EMF plus and minus? When we are moving from plus to minus of a cell, from plus to minus, take it as minus. When we are moving from minus to plus, take it as plus. So that idea for EMF, it's clear. Look, suppose you are moving like this, positive to negative, so it is minus. If you are moving like this, see, in this manner, negative to positive, then take it as plus. Plus to minus, minus. Minus to plus, it should be plus. Okay. Now, these ideas are there with you. Now, I am applying that idea for the loop A, B, C, D, A. Look, so for the loop A, B, C, I said LHS. So, I am writing LHS of my equation where I am taking product of current and resistance only. So, here I1 and here 20. So I can write 20 I1 and here BC nothing. Here CD 40 I2. So plus 40 I2 equal to. So we can say 20 I1 plus 40 I2. Now what I'm saying means, look, we are considering the right side. Right side is EMF. So right side is EMF means I'm taking like this, see, I'm moving from A to B. So I'm moving from minus to plus. Minus to plus. So it will be plus 80. Plus 80. Now I can rewrite I1. I can divide by 20 first. So I1 plus 2I2 is equal to 4. Then I can replace I1. I1 as I2 plus I3. So I2 plus I3 plus 2I2 equal to 4. Now I2 plus 2I2 is equal to 3I2. So we can say 3I2 plus I3 equal to 4. That is equation 1. Now in the same manner, we can find the next loop. That is, look, I'm taking the loop now. DCFED I'm taking. So I can write that is DCFED is there. DCFED. In DCFED, look, I'm moving from D to C. Take care. D to C. Current is moving from C to D. So it is in the opposite direction. So there should be a minus sign. So we can say that is minus 40 I2. Minus 40 I2. And here this I3, now it is in the direction. So 10 I3 is coming. So that is plus 10 I3 is equal to. Now if you are checking here, now look, now the IR part is completed. Now only cell part. The right side is cell. I'm moving D to C. No cell is here. CF, no cell. Moving like this, F to E, I'm finding a cell, but I'm moving from minus to plus of the cell. So we can say, look, when I'm moving like that, I'm moving from minus to plus of the cell. So there is a gain in voltage. So plus 40 it is. So we can say that is equal to plus 40 will be there. So that is plus 40. Now I can divide by 10. So it's coming minus 4I2 plus I3 is equal to 4 is there. That is equation 2. Now here you can see that, look, there is I3 here and I3 here. So we can subtract these two equations. So equation 1 minus 2 implies. So what is coming here now, look, 3I2 plus I3 equal to 4 minus 4I2 plus I3 equal to 4. So simplifying, I3 minus I3 0, 4 minus 4 0, 3I2 minus of minus 4I2, so 7I2 is equal to 0 is there. So we are getting the answer, I2 is equal to 0. So I2 value will be 0. If I2 is 0, then what is the I1 value? Substituting in any formula, I3 value you are getting. Now look, 3 into 0 plus I3 is equal to 4. So we are getting I3 is equal to 4 ampere. So I3 is 4, I2 is 0. So what is I1 now? I1 is I2 plus I3, so that is also equal to 4 ampere. 4 ampere is there. So the very important point, Kirchhoff law related questions are there for examinations. So I1 is equal to 4 ampere is the answer that we are getting here, and I3 is equal to 4 ampere and I2 is equal to 0. I am repeating this point, please listen here. When we are taking Kirchhoff law, sign convention we have to study well. And one more, sometimes our answer will be 0, sometimes our answer will be negative also. If you are getting a negative answer, what does it mean? The direction of current is opposite to the direction of the marked current. So if you mark the current from B to C, then you are getting the current sign is negative, which means current is not flowing from B to C, current is flowing from C to B. That's the point. Current is flowing from C to B is there. So the right answer here, that is equal to, we got I1 is 4 ampere. Now we are explaining the next one, question 13. Now there, the last spell of our discussions now. We have 2 more chapters, important ideas remaining. That is moving charges and magnetism, and matter is there. Moving charges and magnetism, I told in the beginning of this discussion, for moving charges and magnetism, you know, that chapter, the direction ideas are very important. So, in order to solve a problem, we should have the direction ideas. Then only we can solve the problems and to find the answer for particular questions. Now here, the question 13 we are explaining. What is question 13? A neutron and an electron and an alpha particle moving with equal velocities enter a uniform magnetic field going into the plane of the paper as shown. Trace their path in the field and justify your answer. So you know, these are charged particles. Alpha particle is a charged particle, and we can say electron is also a charged particle. When a charged particle is moving through a magnetic field, it will experience a force. So I want to find the direction of that force. Then I can say in which direction the charged particle is moving. If the force is along y-axis, charged particle will move along y-axis. If it is on negative y-axis, charged particle will move on negative y-axis. So I want to find the direction of force. So how I will find the direction of force, that we are going to explain here. So there, you know, we can say the direction of force to find, we have the formula vector F is equal to Q into V cross B. That is the formula, Q into V cross B. So here, you know, we are using actually Fleming's left hand rule. You know, Fleming's left hand rule means, you know, that we are stretch your left hand fingers in such a manner that father, mother, child. So now force, magnetic field and velocity. Force, magnetic field and velocity. Then, so you know, that is the thumb point will represent in the direction of force. But you know, this applying this finger in the exam hall, it may be just like the invigilators may say you are playing Kathak. So some students have a problem to do this one, because you know, they have, for where is the pocket side, you know, see left and right to identify, they will look to the side of pockets. Then only they will identify which side is left and which side is right. Such students are there. So no need to worry. Any student can answer this Fleming's left hand rule questions by using what is, you know, the cross product rules. Cross product rule. We studied vector product, cross product. So we can say, what is the cross product rule here? Now suppose I am considering I, J and K is there. So this is the circle that we are considering the direction sense. So I cross J is equal to K will be there. J cross K will be I, and K cross I will be J. And if you are taking the reverse, because J cross I, that will be coming minus. And we can say K cross J will be minus I. And I cross K will coming minus J. So suppose we are considering vector F is equal to Q into V cross B. Here now I am writing it is alpha particle. So charge is positive. Velocity in the X direction. So I can mark V I cap cross. Why sir I cap? Because you know, it is in the X direction. So I am marking only direction here to find. So no need to mark V here. So please say I am marking I cap cross. Then there is magnetic field. Conventionally, please realize what I am saying. Conventionally, cross represents inward. magnetic field directed into the plane of the body's cross. So we can say, suppose I am considering this cross, it represents inward. Inward means we are considering negative z-axis. Negative z-axis. So I can say I cross minus k. I cross minus k. So I'm taking that minus outside, then I cross k will be there. What is I cross k stands for? Look, k cross I is j. So I cross k will be, what is coming here, see, that is equal to minus j will be there. So it's very clear. I cross k will be minus j, and minus of minus j, so it's coming plus j. So we can say that is, suppose we are considering, the force will be on y-axis. The force acting on this alpha particle will be along y-axis. So we can say, suppose we are considering alpha particle experience force like this. One important point, suppose we are considering this is the force direction. So force direction is like this. Now we can say under the influence of this force, what happened? Charged particle is moving upward. But under the influence of this force, it is not only moving upward, it will move in a circular path. That idea we studied. When a charged particle is moving through a magnetic field and perpendicular to the field, it describes circular path. So we can say this alpha particle will experience a force, and as a result it is moving like this. So the path will be deviating upward. Okay. Now the next one, there is electron. What is the charge of electron? Electron charge is negative. So instead of plus, there will be minus sign. That minus, and already there is a minus sign, so it becomes a plus. Then I cross k, there will be a minus j. So it's the reverse. It's already we know. What is the idea? Means alpha particle is deviated upward, means definitely the electron will be deviating downward. So we can say electron will be experiencing the force downward, so it moves in a circular path and comes out like this. It completes a semicircular path and coming out in the field. Why it is deviating down? Because it is minus j. Electron have negative charge, so minus j. Now we are thinking about neutron. Neutron has no charge. There, what is our basic formula? Q into V cross B. So there is no charge here. As there is no charge, neutron has no force. So we can say this neutron will move along the same straight line, no deviation. Okay, this idea is correct. Alpha particle will have a more velocity, more radius compared to that of the electron. Because see, if you are considering the radius formula, R equal to mv by qb, so mass of alpha will be more, so we can say its radius will be larger. So when we are neutron will be straight line, it is not moving deviated. Alpha will be deviated upward, electron will be deviating downward. I am repeating this direction idea once more. Please listen here. Look, for our examination it will be benefited. If there is a field like this coming, what's the meaning of that? It is outward. So we can say that is denoted by k cap, positive z axis. If there is a field like this, so what is the meaning? Inward, so minus k cap is there. If you have this idea, we can try all questions actually by using this cross product idea, and we can determine the directions. Why they are moving? If you are considering in the, it was, yeah, right. So now look, why we are explaining this point correctly, look, that is when the charged particle is moving in a perpendicular field, it describes a circular path. So deviating up and moving like this. So we can say the path that we marked here correctly. So that's the point for this the question now. Now we are explaining question 14. Another important question for examinations. Another important question. Most possible question for the upcoming exam. So question 14, look. Two identical coils P and Q, each of radius capital R, are lying in the perpendicular planes such that they have a common center. Find the magnitude and direction of the magnetic field at the common center when they carry current equal to I and root 3I respectively. So it's a question repeated many times in the examination. So now to find the magnetic field at the common center of the two circular loop. So how we will work out? There suppose we are considering at the center there will be two field. Two magnetic field. Field due to the circle P. Field due to the circle Q. Because two circles, so two field. So what is the field at the center due to the circle P now? So we can find the direction first. What is the idea to calculate the field direction now? We studied when current flows in clockwise direction, magnetic field will be directed inward. When current flows in anti-clockwise direction, then magnetic field will be directed outward. So we can say clockwise field will be inward, anti-clockwise field will be outward. So here look, the current flowing which direction? Look, current flowing in this diagram, you see current is flowing like this. So it is in anti-clockwise direction. So field will be directed outward, which means from the plane of this one directed outward. So marking, this is the magnetic field due to the loop P, BP. Now here look, here the loop is there, current flowing which direction? Look, current flowing here also anti-clockwise in the loop Q. But here we have to visualize loop Q, that is like this in this plane, and the current flowing anti-clockwise. So field will be outward. So we can say the field will be directed outward. So marking, this is equal to BQ now. So what is the angle between these two fields? 90 degree. 90 degree. So we can find the resultant. So how we can find the resultant? We are completing the parallelogram. So the diagonal will be the resultant. So this is the net magnetic field. Net magnetic field. So I'm repeating once more. We have two field. Field due to the loop P and field due to the loop Q, BP and BQ. And this BP and BQ are in perpendicular directions. So by using the parallelogram method, we are finding the resultant magnetic field, the net magnetic field. Now here we have to find each one separately. What is the equation for magnetic field due to a circle at its center? Mu naught I by 2R. Magnetic field at the circle center, mu naught I by 2R, where R is radius. So we can say magnetic field at the center of the circle due to the field P, BP. So mu naught, the current flowing in P is I. So mu naught I divided by 2R. Radius is R given. Now field at the center of the loop Q, it is mu naught. The current is root 3I. So root 3I divided by 2R. So we have a BP and BQ. If we have a BP and BQ, we can find the net field. How we can find the net field? We studied the parallelogram law. So we are writing the net magnetic field is equal to root of, BP square plus BQ square. I'm not writing the third term. Why I am not writing the third term? Because third term is 2 BP BQ cos theta. We know cos 90. Cos 90 is 0. So we can say that is equal to root of BP square plus BQ square only. These values are there. So I can write that is here, look, that is root of, I am writing now, that is equal to root of BP is mu naught I by 2R the whole square, and BQ is mu naught into root 3 I by 2R the whole square is there. So here, we can take common term outside, mu naught square, I square, 2 square, R square, under root. So mu naught I by 2R I can take outside. Root of 1 square plus root 3 square is there. So that is mu naught I by 2R, then root 1 square plus root 3 square means 1 plus 3. So that is root 4. Root 4 is 2. So mu naught I by 2R into 2. So 2 and 2 cancels. We are getting mu naught I by R. So the magnetic field at the center will be, we can say mu naught I by R. That is the net magnetic field at the center now. Now the question, if this is the net magnetic field at the center, B net is equal to mu naught I by R. What is the direction of this one correctly? Look, direction of the magnetic field I want to find. Magnitude and direction. So how I will find the direction? Dear, in order to find the direction, I am seeing how much this is inclined with the x-axis. So this angle I want to find, alpha. Can you say how I will find alpha? Tan alpha is opposite by adjacent. Look, opposite is BP. So I can say tan alpha is BP by BQ will be there. So I can write here. So to find the direction, so I am writing for directions, the picture clear, tan alpha is equal to, we can say in our diagram, what is opposite side, BP and BQ. So that is BP divided by BQ is there. So BP value, please see. BP value we have correctly, BP value that is mu naught I by 2R and mu naught root 3 I by 2R. So these values I am substituting here. So mu naught I by 2R by mu naught root 3 I by 2R. So mu naught I cancel, 2R cancels, 1 by root 3. So tan alpha 1 by root 3 means alpha is equal to 30 degree. So we can say alpha is equal to 30 degrees there. So this is the point correctly, look there, here, that find the directions of this one. This circular loop problems are very, very important for exam. Very important. See, this point is we completed. Now we are explaining question 15 now. What is question 15? If a conducting wire is bent in the shape of a square and another wire of equal length into a circle, if they carry currents, their magnetic moments are in the ratio. Dear, we are talking about magnetic moment. What is the equation for magnetic moment? Magnetic moment is NIA. NIA. So here, look, another. So there is a wire. Its length is L. It is bent in the shape of a square now. Look, it is bent in the shape of a square. Suppose side length A. And then there is another wire. It is bent in the form of a circle now. Circle. So suppose its radius is R. Now we are saying what is the ratio of magnetic moment for square and circle. So magnetic moment of the square I am finding first, MS. S stands for the square now. Okay, look. So what is the point there means, it's NIA. There is no number of turns. It's simply only one turn is here. So I into area of the square is A square. So I A square. I want to change this A in terms of length. So how this is possible, L becomes 4A. You know, this length becomes 4a because length becomes circumference. So A equal to L by 4. So I can write ms is equal to I, a square. So L square by 16. So that is ms, magnetic dipole moment of the square now. So what is magnetic dipole moment of the circle? So current I, circle area pi r square, pi r square. Now I want to find this r in terms of L. So L equal to circumference 2 pi r. So r equal to L by 2 pi. Substituting that. So MC is equal to I pi into L square divided by 4 pi square is there. Now cancelling the terms. Here you know r square. So we are simply squaring them. So we can cancel the terms here. We can say here this pi and pi cancels. 1 pi cancels, you know. Pi and 1 pi cancels. So the answer is coming. Magnetic moment of the circle is I L square by 4 pi. So that is equation 2. Find the ratio now. So ms by mc we are finding. So we can say ms by mc is equal to, for ms what is I L square by 16. So I L square by 16. And mc what it is? I L square by 4 pi. So I L square by 4 pi. So 4 pi by 16. Pi by 4 is the ratio. So the right option we can say pi is to 4. Yes, right. The right option is option B. Pi is to 4 is the right option is coming. So this is the right answer. Pi is to 4. The right answer is CSMTK, right? So that is the right answer is pi is to 4. Okay, now we are explaining the next question correctly. So look there. A short bar magnet, question 16, last point, last 5 minutes, there we have to do, you know, actually only 2 more questions correctly. That is the end of the questions. Before that, the 19th one is actually chapter 1. You know that is, the electric flux depends upon what? What it depends upon? Net charge enclosed and permittivity of the medium. Right answer is option A. Okay. Now we are explaining their magnetism and matter question. I can give you a very important hint, or I can leak the question paper. What saying? What saying? I can leak the question paper on March 6th. See, you know, that is in the chapter, so now it's very important. In the chapter magnetism and matter chapter, there will be a numerical problem. That numerical problem will be textbook based numerical one. It will be a 2 mark questions. So there will be a textbook based numerical problem for 2 mark questions from the chapter magnetism and matter. So here we can consider, what is that question here coming? A short bar magnet of magnetic moment. So magnetic moment given 0.32 Joule Tesla inverse 1. Uniform magnetic field is given 0.15 Tesla. Free to rotate in the plane of the field. Which orientation which corresponds to its stable equilibrium? Everyone knows stable equilibrium means theta equal to 0 degree. But we have to say that answer correctly. So, you know, we have to draw that diagram. So, how the meaning of that? What is the meaning of theta 0? Dipole moment and external field should be in the same direction. So, imagine if this is the external field. So, marking external field. In this external field, you are keeping the magnet like this. So, this is the magnet. Dipole moment should be in the same direction. Dipole moment is directed from south to north. South pole to north pole. So we can say Here south and here north. So this is the direction of dipole moment. So dipole moment and field are in the same direction. They are asking, so this is stable equilibrium. Stable equilibrium. And you know, in stable equilibrium, they are asking what is the potential energy. So you know, the potential energy in stable equilibrium, U is equal to minus mb cos theta. That is the formula for potential energy. So we can calculate what is the minus mb cos theta. Magnetic dipole moment is given 0.32 and the magnetic field is given 0.15. Cos 0 is there. So we can say minus 0.32 into 0.15. So the value, when you got the answer, that is 0.048. Minus 0.048 joule is the potential energy in stable equilibrium. Now, unstable equilibrium is there. What is unstable equilibrium? Unstable equilibrium means theta equal to 180 degree. So we can say the same idea we studied actually in the chapter electrostatics also. So we can say unstable equilibrium, that is B. Unstable equilibrium. So unstable equilibrium means we can say that is theta equal to 180 degree. Theta 180. So how I will mark that? I can mark external field. External field. This is the field externally, external magnetic field. In this field, I am ready to place the magnet. But in which direction? Opposite of before. So here we can say north and here we have a south pole of the magnet. So the dipole moment is directed like this. So we can say it's opposite to that, theta 180 degree, unstable equilibrium. Potential energy formula already we know. U equal to minus mb cos theta. Many got the answer right. So we can say m value is there, theta value cos 180 here. So minus mb cos 180. Cos 180 minus 1. So that is equal to mb. And this value we calculated just before. Minus of 0.048. So it's simply 0.048 is there. 0.048 joule is the potential energy. So please listen here. This is the last question that we are solving today. So please see, we completed all the 5 chapters. Very important, most possible, most probable questions that coming for the March 6 examinations. So focus on this area. Watch the video many times and make it clear. I'm requesting how we have to use the remaining days correctly. So now we have 3 full days are there. 3 into 24 hours are there with you. I'm saying the last day, that is on Sunday, don't do any extra things. Any things no need to study on that day. Sunday completely revisions. Sunday early morning till you are going to bed, start the chapter from the last chapter start first. That is solids and semiconductor chapter. I think you all have a well-known checklist that we send in the group. So from that checklist, you can study each and every point and feed them in the brain, see, as layer by layer, just like how we are arranging a books in a shelf. Datas, you can arrange them properly on Sunday. And I'm saying, that day before Sunday, that is on Saturday afternoon onwards, I'm requesting to all of you, start to write derivations. We have around 29 derivations are there, 29 derivations only. So all the derivations, if to answer difficult questions, derivations, if we are struggling to complete, we will not get time to break unknown questions. So the derivations we want to go smooth, very smooth and very fast. It is possible by revising them. So Saturday afternoon, spend to complete all derivations, all statement like that, writing again, practicing. Tomorrow and the day that is, half of that Sunday, spend yourself, Saturday, half of Saturday and tomorrow full day, spend on previous papers. Previous papers are very important, at least last 5 years. I can assure you one thing, if you complete last 5 years board examination numericals thoroughly, you will not worry in numerical in the upcoming exam. So numericals are strictly coming. So, number may be changing, 2 numerical may be mixing as coming as a 1 numerical, or concept may be mixing, but the content, the idea of the question will be for past year papers. So last 5 year all chapter numericals you have to be thoroughly know, and then derivations, and the Sunday prepare well. I'm wishing all of you, all of the students attending the online sessions here or not attending the online session here, all students, we are on the behalf of Brilliant. I'm wishing you a very happy success and make it perfect. We are with you, the team Brilliant. Thank you. I'm Muhammad Shamim signing off.
Brilliant Qatar, your trusted coaching partner for IIT, JEE, NEET, Science and Commerce tuitions with 10 years of excellence in quality training. Brilliant Qatar.